this is an introduction to the imaginary number I. So, normally, if we take a number such as the root of minus 16, and you type that into your calculator, you're going to get a math error. And this is because there's no two real numbers that you can times together to make a negative number. As if you take minus 4 and square that, you'll get positive 16, and if you take 4 and square that, you'll get positive 16. Which leaves us in a problem for what this is equal to. So our first step is that we'll separate it into the root of 16 times the root of minus 1, which, using surd rules, we know is true. From there, we can simplify that to 4 root minus 1. And this is where we'll show you the biggest rule in imaginary numbers. And this is that, I guess, mathematicians decided that they'd let the root of minus 1 equal I. And that's a very important rule. So if you're writing notes, I'd put a big box around that. So, using that, we know that the root of minus 16 is going to be equal to 4i. And likewise, the root of minus, say, 36 is equal to the root of 36 times the root of minus 1, which is 6 times I, so we have 6i. So that's a brief introduction to the imaginary number I. Now, if we take a quick example of a quadratic equation, so that's x squared minus 6x plus 13 is equal to 0. Now, I don't think this can be factorised, so we'll put it into the quadratic formula. So we'll get x equals 6 plus or minus root of minus 6 squared minus 4 times 1 times 13 all over 2 times 1. Now this simplifies down to 6 plus or minus the root of minus 16 all over 2. And here, using our imaginary number, we can split the root of minus 16 into 2 surds, which would simplify to 4i. So you have 6 plus or minus 4i over 2 equals x. If we quickly simplify that, we get 3 plus or minus 2i. And this here is a complex number. So if we take one of those solutions, x equals 3 plus 2i, I'll show you that another rule in complex numbers is that this 3 here is called the real part of our complex number here, and this 2 is the imaginary part. And that's a brief introduction to complex numbers.
Okay, so now's the section on the arithmetic of complex numbers. Okay, so first of all, we need the standard notation for writing complex numbers is z equals. Now would be possibly a good time to point out that often z's can look like 2's, so it's often good to find a way to differentiate your z's from your 2's, so I like to do squiggly z's. In this case, z will equal 2 plus 3i. But we want to be adding two complex numbers together, so the standard notation we will use for a second complex number will be w, which in this case equals 5 minus 2i. So to add z plus w, first of all we split them up into what they look like as complex numbers, so it's 2 plus 3i plus 5 minus 2i, which then we separate them into real and imaginary parts, so which is 2 plus 5, 3i minus 2i plus them, which becomes 7 plus I, which is z plus w. Okay, to times, okay, have you got that? So to times imaginary numbers, zw, it's the same, you write them as their, as their complex number forms, 2 plus 3i, 5 minus 2i, which then becomes 10 minus 4i plus 15i minus 6i squared. And so, okay, so now we know that since I is the square root of minus 1, therefore I squared equals minus 1. So this becomes 10 plus 11i plus 6, which then becomes 16 plus 11i. So that's how we do, that's how we multiply complex numbers together. And we can use this in simultaneous equations. So let's say our first equation is 3z plus w, which equals 11 minus 10i, that's equation 1. And then z plus w equals 5 minus 2i. Okay, so now we subtract equation 2 from equation 1, which becomes 3z plus w minus z minus w, which equals 11 minus 10i minus 5 plus 2i, which means that 2z equals 6 minus 8i, which means that z equals 3 minus 4i. And then we substitute this into our equation 2 to find the value of w, which means that 3 minus 4i plus w equals 5 minus 2i, which means that w equals 5 minus 2i minus 3 minus 4i, which is 2 plus 2i. Yes, therefore z equals 3 minus 4i and w equals 2 plus 2i.
Normal numbers, real numbers, are represented on number lines. You would get a line like this, possibly 0 in the middle. You'd have 1, 2, 3, minus 1, minus 2, that's not a minus, minus 2, minus 3. That's how you would represent numbers. Complex numbers cannot be represented on a line. They have real parts and imaginary parts, and therefore have to be represented in 2 dimensions, like this. You would have your normal number line of real numbers going along here, real. You would have your imaginary numbers up here. So, to plot a number on an Argand diagram, this is called an Argand diagram. Say I want to plot the number 3 plus 2i. I would take 3 and I would go up here 2. I would find the point and I would draw an arrow to the point, just as a vector. If I wanted to represent on the same diagram, say minus 3 minus 2i, I would go minus 3, minus 2, find the point, and join them up with an arrow. Now, these, just like vectors, can be added. Obviously, if I add these two, I'm going to get 0. An easy way to add complex numbers, just as vectors, is tip to tail method. You put the tip of one arrow on the tail of the other. So if I wanted to do this with some other numbers, I'll take 3 plus 2i, not to scale, and 2 plus 3i, I would take this one and put it on this one, and that would give me 5 plus 5i. My graphs have merged. So this vector here is 5 plus 5i. Complex numbers have special properties, which are best shown on graphs. These properties are the modulus and the argument. The modulus is simply the length of the line, and this can be found using simple Pythagoras. If I take the line again, 3 plus 2i, I would take this height, 2, and this length, 3, and I would use these to solve Pythagoras. I would get the length z, complex numbers represented by z, equals the square root of 3 squared plus 2 squared. So z equals the square root of 9 plus 4. Z equals the square root of 13. Modulus of z, represented like this, equals the square root of 13. The argument of z is the angle. If I take 3 plus 2i, 3, 2i, it is this angle here, which I shall represent theta. So, this is the argument of z, written arg z. Argument of z is this angle, and it can be found by doing tan minus 1 of the imaginary part, in this case 2, divided by 3. I don't have a calculator on me, but you can work that out. That's it.
Oh, no, now. Applications of imaginary numbers are in all sorts of all different parts of everyday life. For example, they're used in cartography, which is map making, so anytime you're using maps, you might come across imaginary numbers if you look hard enough. Telecommunications, any type of signal processing, so control system signals, so I'm guessing that could be to do with planes. So they are quite helpful and they're not completely pointless. Okay.